Hello guys, welcome to the second episode on the guided tour of Lux. On this episode we're going to be checking out what are the basic data types that Lux has got to offer, how to make functions, some other functionality that pattern matching provides, and before that we're going to see how do you get this nice coloring in your source code. Well, this is done by using lux-mode. I don't know if I mentioned that in the previous episode. Lux-mode is an Emacs mode. This is Emacs for those of you who don't know. And lux-mode is an Emacs mode that gives you all the nice indentation, coloring, everything you need. It works well with ParEdit, which is a great tool for Emacs for working with Lisps, and with Rainbow Delimiters mode, which is what I use to have this colorful parentheses. Here there is a repo on my GitHub account, and it contains information about how you get to install it. It's pretty easy, pretty simple. You're gonna be ready pretty soon, and it is updated for version 0.3.3. So it has coloring for a variety of macros and has proper indentation for all those macros too. So by the way, functions, there is no coloring for functions or constants in Lux, only for macros and for literals. So that's why you might never see like functions like map or something like that getting coloring. But anyhow, let's talk about types in Lux. Well, as it turns out, Lux offers 5 different kinds of primitive types, 2 different kinds of composite types, and then it also offers you a way to use all of the possibilities of the types of the host platform. So as you might know, Lux runs on the JVM, so you can actually access any class, object, anything from the JVM. You can invoke methods, you can create new instances of objects, access their fields, all that kind of stuff. And there is even a module that gives you a variety of tools for doing that very easily and a way that interfaces very well with Lux, which is the host module that we can see over here. Now right now we're not really making much use of the host module, and we won't for this episode, because the episode in which we're going to be using host interrupt is going to be a later one. But at least now you know that in the Lux host module, that's where you go to for working with the JVM. So the 5 primitive types that Lux provides are pools, which kind of look like your traditional Boolean values, true and false. You have int, which are just your numbers, very simple. You have real, which are what most other languages are called floats or doubles. Then you have chars, which are your regular characters. They don't have the same syntax that you see in most languages, which use tend to use single quotation marks, or in the case of closure, they tend to use backslash and then the name of the letter. Instead of that, you have something like the normal string literal syntax in most languages and a hash sign at the beginning. And for those of you who are familiar, it's kind of like the same syntax that closure uses for regular expressions, except that these are not regular expressions. And finally, you have text, which looks like this. It can have spacing. It can be multi-line, by the way, which is really nice. But there is a caveat, which is that for multi-line text, it must always be formatted so every line is always begins at the same column as the first line. The reason is that without that, you will end up with something like what closure has, which is that if you want to use multi-line text, you gotta do something like this. Like the first line starts whatever you want it to, but every other line has to start as column 0, which is really bad. It looks really bad when you're reading the code. It's not a nice thing to see, and there is like this disconnect between what you would like to see in the code versus what's gonna get printed if you print it to standard output or something like that. Instead, Lux requires that everything is matched, and that way, your text is gonna look in your source code the same way it's gonna look wherever you use it, which is a really nice property to have. But if you have like empty lines between your lines, they don't have to be matched by columns. They don't have to be, because it will be like an inconvenience. You don't need to do that. Also, now we're talking about syntax. I don't remember if I mentioned in the previous video how do you do comments in Lux. This is a single line comment, and this is a multi-line one. And by the way, multi-line comments can be nested, which is really cool, just like in Haskell. So yeah, from what I can see, the editor, well, the lux-mode apparently doesn't handle that very well, because it has assumed that there was some parentheses there. Doesn't matter. There are just things that need to be polished in the lux-mode. But Lux supports multi-line comments, which is the important thing, and single line. So before I go into the composite types, I would like to make something clear about the names of the types, of the primitive types. You might wonder, if Lux compiles for the JVM, why doesn't it use JVM primitive types? And the reason for that is very simple. One of my original intentions with Lux was to make it a multi-platform programming language, and in order to have a very smooth experience in that, especially considering that people might want to be able to reuse libraries across different platforms, like write your library once, but it runs in the JVM and it runs in JavaScript just the same. People might want to do that. And if I rely on the primitive types of each platform, that's gonna be very difficult, because they don't tend to match. Like, you have 4 different integer types on Java and 2 different floating point types, but in JavaScript you only have number, which is always a double. There are no integers, everything is number. So if I needed to find some way to have like a standard set of primitives that I could rely on every platform, regardless of how they ended up being implemented in the end. Because when I eventually compile Lux programs into JavaScript, reals and ints are actually just gonna be numbers, because there's no other choice. But that doesn't mean it's a detail that has to impact Lux. There can be ways to kind of buffer Lux from all the irregularities between the platforms, and so having this set of standard types kind of seemed like a good idea. A boolean type that you can rely on different platforms, an integer type that you can rely on different platforms, reals, chars, text. And since I was already gonna come up with my own different ways of handling primitives across platforms, I figured if I'm gonna be having my own types anyway, I might as well give them names that I like. So boolean got shortened to bool because it's shorter to write. Int, it's kind of obvious. Real, I wrote it because I kind of don't like the idea of naming your types based on implementation details, and that's what the names float and double are. They don't reflect what the thing is, they reflect how it is implemented in the machine. So I decided, hey, we're working with real numbers, so let's just call them real. Char, pretty simple. And text, name it that way because string, when I think of a string, I think of a string. I think like a rope or a strand of some fiber. I don't think of text. Text is text. The name string, as far as I remember, comes from assembly programming. It was a way of naming arrays, and since text tends to be implemented as arrays, the name kinda got stuck. I don't know if that's the real story, but that's the one I learned. But I decided, what? Let's just name text as text. I don't care how other platforms name them. I'm gonna go with the obvious, simple name. Now, now that we have this explanation out of the way, I'm going to explain, how this maps to the JVM. This maps to the java.lang.boolean class. This here maps to long. This maps to double. This goes to character, and as you can imagine, this goes to string. Simple as that. So these are the 5 primitives that Lux provides. There is another primitive that Lux provides, but it's kind of magical, and we're gonna see it when we talk about the composites, which we're gonna do now. So these are the simple ones. And I'm gonna talk about the composite types. So there are 2 main composite types. There are variants and tuples. So a tuple is, the way most people think about it is simply an ordered and limited sequence of heterogeneous elements. So it will be something like 1, 2.0, 3, 4, say true. Let's say that true is our 5. So we have this 5 tuple containing elements from all the primitives that we mentioned. It can contain composites too. It can be something like this, up to arbitrary levels. It can be something like this and whatever. It can be anything you want. But the point is just an ordered and limited sequence of heterogeneous elements. It could be the same elements if you want to, but doesn't need to be the case. Variants, on the other hand, they can only contain one element. But the thing about variants is that, in the same way that tuples allow you to have multiple elements at the same time, variants are kind of like the opposite. They give you the ability to choose one option among many different options. Like in tuples, you get everything at the same time. You get all options right away. In variants, you get only one, but there are many others. There could be possibly as many as you want, but you get one, and you get a way to differentiate between which one it is to know which one you're working with. So it will be like something like, for instance, a variant type is the list type, which is defined as the type list of A. It is polymorphic, and we have nil and const of A and another list of A. So for those of you who might not be familiar with type systems of functional programming languages, I'm going to explain more in detail what this means and how this works later on. But right now, let's just say that a list is defined as nothing, which is nil, or as a pair of an element. Well, that is what const is, a pair of an element and the rest of the list. The element is called the head of the list, and the other list is called the tail. So we have the head and the tail. So this is a variant because it contains 2 alternatives. I can either have an empty list, or I can have a list that contains at least one element, which is the const. But I cannot have both. A list cannot be both empty and containing something. So it will be a variant. Now, there is another kind of data structure that Lux provides, but it's actually more of an illusory data structure. It's not real. It's actually something that maps into something else, and that is records. So let's say that I want to define something like, let's say that I have a program that has users, right? So I want to define a user type that contains user information, right? So I'm gonna go with this user. The user has a name, which is text. It has an age, which is an int. I don't know. I want to know if the user is alive, maybe it could be dead, right? So I have a boolean field. Well, this is a record. The way I will make an instance of this will be with something like this will be an instance representing myself, right? But how does this get implemented? Is this, I said that this was an illusion, and it is. What actually ends up happening is that the Lux compiler, he checks out the tags that you're using, which are these things here with the hash sign. It checks out the tags. Every tag gets assigned an integer value representing the order in which it appears in the type definition. So name will have 0, age will have 1, and alive will have 2. And knowing the order, it can actually transform my record into a tuple. So all records are tuples, not just in every single way. There are no record types in the Lux type system. There are only tuple types. And when records get compiled down, they get compiled down in the exact same way, and they get analyzed by the compiler in the exact same way as tuples, because they are tuples. They are tuples with fancy syntax to make them easier to work with. Simple as that. Now I'm not going to explain in this video how does Lux compile the data structures, which is very interesting, at least to me. But maybe I'm going to talk about that in a future video. Right now, let's just say that Lux does a good job, an efficient job at compiling things down, and everything is efficient and simple and whatever. So here we have our functions. Now we have talked about the data types. Let's talk about functions. It's a very important thing. So I'm not going to talk about other things you can do with functions, because there are many. But let's write some simple function and see how it looks like. So we're going to write a factorial function, a classic functional programming example. So to define things in Lux, you use the def macro. Def type, by the way, is based on def. I'm not going to explain how, because that's going to be left for the episode on macros. But let's just say that you can define certain primitives of the language in terms of others. So with def, I can define functions. Let's say factorial of n. So since this is a typed programming language, let's give our function a type. Our function is going to be a function of int to int. Very simple. You give me an integer, I'm going to give you its factorial. So how do we do this? Well, in the same way we use pattern matching on the previous episode to work with the list of arguments to our program, we're going to use pattern matching on our number. So if it's 0, we're gonna say that this is going to be 1, and if it's different than 0, maybe pattern matching isn't such an efficient way of doing this here. There aren't that many options. Let's just import something from the numbers module. We're gonna go with a number implementation of ints. So if integer equality of n, screw it. What happens if we get a negative? If n is less than or equal to 0, I'm gonna say 1. Otherwise, we're gonna multiply n by factorial of n minus 1. There is the decrement function, which comes from the prelude, or the Lux module, and that's how we're gonna do it. So here we have our factorial, and let's use it. Instead of printing this, let's say we're just gonna print. By the way, I'm gonna show you a nice, cute little trick. You know what? Forget this. Oh, sorry, I used something that I wasn't supposed to do. A little anachronism. The text format module doesn't exist for 0.3.3. That's a 0.4 addition. Sorry, I forgot. So we're gonna have to do it the old-fashioned way. Five. This should be 120, which is the factorial of 5. And let's delete all of this. You know what? Yeah, forget it. Let's delete it. And oops. Let's compile this. By the way, I deleted the cache from yesterday, so now it's compiling everything from the beginning. So let's just wait until everything gets compiled, and we're gonna be able to see the factorial. There we have it. And we have 120, just like that. Now, there are some interesting things that we can see in this function definition. You know, besides the fact that I had to import the number implementation for integers and the show implementation for integers too. The show is what gives you the ability to turn something and make it into a text for logging, for instance, in this particular case. And you know, number contains, you know, multiplication, division, those kinds of operations, you know, comparisons, equalities, you know, the kind of operations that you would expect for numbers. So what do we have here in our factorial function, right? So here we have this this syntax, you know, the name of the function followed by the different arguments. Here we have the type. This is the way in which you write types of functions. You know, you have this little arrow. Then you can have an arbitrary number of arguments. It could have been something like, you know, you could have like an arbitrary number of arguments, which of course you're gonna have to match over here. In this particular case, we're only taking one, so only this int. And the last thing you put here is gonna be the return value. So we're taking one int and we're returning another int. Now there is a little bit more complexity to writing types, but we're gonna explore that with more detail tomorrow, as we talk with more detail about the type system and what does it contain and how everything works. For now, let's keep examining this function. So here we have an if statement, which an if expression, which is really interesting because previously we saw pattern matching. We saw the case expression. Well, if is actually implemented in terms of case, because case can pattern match anything. You can analyze any piece of data that you get. If, on the other hand, is constrained to only work on booleans. But since case can be used for anything, if case just implemented in terms of case. And it works for a very simple case of what happens if I have one boolean expression and I want to do something if it's true, and I want to do something if it's false. You know, if then else. So here we have our test expression. This is our then expression, and this here is our else expression. Now we also see something really interesting here, which is that we have a call to the function itself. This is called recursion. For those of you who might not be very much familiar with that technique and who might not be very much familiar with functional programming, recursion is the capacity of a function to use itself. It's kind of like a loop, except that it has less rigid limitations than loops in object-oriented programming languages or imperative programming languages. So here in factorial we're saying, hey, if we have a number that is 0 or less, we're just going to give 1. Technically there are no factorials for negative numbers, but since integers can cover negatives, we're gonna pretend that the factorial of negatives is also 1. And for positives, what do we get? Well, multiply n, which is the number we got, by the factorial of the lesser number. So we will have something like, well, we will have something like factorial of 5 ends up becoming 5 factorial of 4, which ends up becoming 4 factorial of 3, and so on and so forth, until we end up with 3 2 1, and this will actually be 1, which is, we have the 5, the 4, 3, 2, 1, and this other one is from 0 or less. Multiply everything, you get 120. Simple as that. Now, since I mentioned that you can use recursion for loops, you might wonder, well, but can I also have like normal loops on Lux? And the answer to that is yeah. There is a looping macro, but we're gonna see that one and explain how it works in future videos. So for now, what do we have? Well, we can write functions, very nice. I'm not gonna explain how to write polymorphic functions right now because I'm gonna leave it for tomorrow. But well, now we have functions, and well, I mentioned that I was gonna talk about pattern matching on this video, but now that I think about it, the video has already extended a bit, and pattern matching in Lux is maybe a little bit advanced, especially because of some of the extensions that Lux has available. So let's say that we're gonna leave it for another episode. So here we have learned about what are the basic and not so basic types in Lux, how to write functions. We have seen lux-mode, and before I forget, I forgot to talk about how to use host types in Lux. Well, we're gonna leave the advanced stuff for the Lux host module video, but suffice it to say that you can transform normal Java types into Lux types using a simple macro. So if since I mentioned previously that int is actually defined as java.lang.long, I could say something like this instead. This caret is actually a macro that, given the name of a class, transforms it into a Lux type. And since integers are just longs, that means this has to compile. And indeed, it does. We run it, we get the same result. Very simple. Now, you can add, this macro can be a little bit more complicated. You can add like arguments, like for instance, if you want to have something like a Java list of longs, for instance, you could do it that way. But for cases in which you're dealing with types that don't have parameters, you can forget about the tuple syntax there. Although you can add it if you want to. It's just you can omit it if it's empty. Now I guess that's it for today. Hopefully we'll talk tomorrow about types. Maybe we'll finally talk about pattern matching. I don't know. Let's see how it goes tomorrow. See you then.